Hello there, and welcome back to Power Series Representation Part 2. This is Lecture 27 in our Calculus 2 series. So I'm going to start with my first example of finding a power series representation for tangent inverse of x. And recall that the other way you can write this is arctangent of x. So those are both the same thing. So in order to do this, I'm going to use strategies from Lecture 26. So we're going to recall that f prime of x, the derivative of arctangent of x, is 1 over 1 plus x squared. So that is a rule from Calculus 1. Then I'm going to start manipulating this so that I can use my geometric series from the last video. So this is 1 over 1 minus a minus x squared. And then using our geometric sum formula, this is equal to the summation n equals 0 to infinity. And this time I'm plugging in negative x squared to the n. But then this is just n equals 0 to infinity summation negative 1 to the n times x to the 2n. And then this is true. So the interval of convergence for this is true when we're strictly between negative 1 and 1 for x. Now we make the observation that since the integral of f prime of x dx, so this integral is equal to arctangent of x plus c. So that's what you get when you integrate 1 over 1 plus x squared. So since that's true, we have the following. So we have that tangent inverse of x is going to be equal to the integral of f prime of x dx. However, we calculated that f prime of x dx is represented by this series here. So instead of f prime of x dx, I'm going to plug in the series, which is summation n equals 0 to infinity of negative 1 to the n times x to the 2n. And then we learn that you can integrate this term by term as long as you're within the interval of convergence. So to integrate this with respect to x, I increase the power by 1. So I'm going to get summation n equals 0 to infinity. I'm going to increase the power by 1, and I'm going to get negative 1 to the n x to the 2n plus 1. And I'm going to divide it by 2n plus 1. So I just did the power rule backwards. Negative 1 to the n is just a constant, so that doesn't come into play. And then I get plus c, because I integrated and it's an indefinite integral. So I have the integral, the arctangent of x is equal to this here. And I'd like to determine what this c is. So what I could do is I could plug in x equals 0 into this equation to figure out what that constant c should be. So if you plug in 0 for this x right here, you'd get that this would be the 0 series. It would just be 0 plus 0 plus 0. And over here, arctangent of 0 is 0 as well. So I get the left side is 0 equals, and then I have 0 plus c. So this just lets me know that c is 0. So what I could really write here is just that arctangent of x is just this series right here, because c is 0. OK, and then one last thing I'd like to point out is that the interval of convergence for this series here was from negative 1 to 1. However, the interval of convergence for arctan of x is going to be from negative 1 to 1 inclusive. And that's because if you let x equal 1, or if you let x equal negative 1, in the original series, I'll do the first one. So if you plug in 1 into the original, into this series right here, this is n equals 0 to infinity, negative 1 to the n, and then 1 to any power is 1 over 2n plus 1. This is a convergent alternating series. So remember last time, I mentioned that if you integrate a given series, you'll keep the same radius of convergence, but you might also add on the endpoints to the interval of convergence. So this is a case where we go from -1 to 1 non-inclusive, and then both of these, when I plug in 1 and -1 into the x value here, you get two convergent alternating series. So the interval of convergence for arctan of x is actually -1 to 1. And then here's the series representation right here. OK, so that was just another example of showing you power series representation. Let's use what we just found to find a power series representation for arctan of x over 3. Well, all you have to do here is use our formula for what I just had for this. So we know now from the previous part that arctan of x is summation n equals 0 to infinity, -1 to the n x to the 2n plus 1 over 2n plus 1. So therefore, this is true from -1 to 1. That's its interval of convergence. So therefore, to get this series, arctan of x over 3, all I do is I plug in x over 3 in for x here. I just replace it. So this is summation n equals 0 to infinity, -1 to the n. Here's my x. I'm going to replace it with x over 3 to the n plus 1, 2n plus 1 over 2n plus 1. And then this would be my series. I guess I could just leave it like this. However, I should note that in this original series, x needed to be between -1 and 1. Now, for my interval of convergence, I need to ensure that x over 3 is between -1 and 1 inclusive here. So what that means is that the interval of convergence for arctan of x over 3, if I multiply everything by 3, I get -3 inclusive to +3. So this is a representation for arctan of x over 3, just by plugging into a known power series representation. And now my final example here says express pi as the sum of an infinite series. So for these kind of questions, you need to make use of the well-known values for the function you're given. So for example, my observation here is that arctangent of 1, what angle would that be? That would be pi over 4, right? Remember, tangent of pi over 4, that is 1. So arctangent of 1 is pi over 4. So this is kind of the key. You need to make an observation like that. And then let's look at my series representation that I have. So arctangent of 3 over 3. So 3 over 3, that is 1. So this is equal to pi over 4, right? Arctangent of 1 is pi over 4. But what else is this equal to? Well, if your x right here is a 3, that's what I plugged in, x is 3, and it's in the interval of convergence, so I'm allowed to plug that in. That 3 is in the interval of convergence. Let's plug a 3 into the series here. So this is equal to the summation n equals 0 to infinity. I have -1 to the n. And now I'm going to replace this x with 3. So then I'm going to get 3 over 3 is 1 to the 2n plus 1 over 2n plus 1. And then finally, if I want to figure out what pi is as an infinite series, remember this series is equal to pi over 4. I just need to multiply both sides by 4, and then I have the representation. So if I multiply both sides by 4, I get pi is equal to 4 times summation n equals 0 to infinity, -1 to the n. 1 to any power here is just going to be 1, so I'm just going to not write that. This will be 2n plus 1. And if I go ahead and write the first few terms of this, just to show you what pi looks like represented like this, if you plug in 0 as your first term here, you get 1 over 1. And if you plug in 1, you get -1 over 3. And it's alternating. It keeps going back and forth. So then it'd be plus, for 2, you'd get +1 over 5. So the idea is you can represent pi as this infinite series. It's 4 times 1 minus a third plus a fifth minus a seventh, and that will also equal pi, represented as a series. So kind of cool to see that. OK, so in the next part of this video, we will be doing some more practice with power series representations. We're going to be finding another power series representation for more practice, and we're going to be using them to estimate the value of a definite integral. So I'll see you in just a moment for that. All right, welcome back. So we're going to do another example where I find the power series representation, and this time it's going to be of log of 3 plus x. You may want to pause the video and try doing it yourself and see what you come up with. But I'm going to go ahead and get started. So again, I'm going to make an observation here. So I'm going to observe that the derivative of ln of 3 plus x, this derivative is 1 over 3 plus x. And I get nothing else from the chain rule. So it's important to make this observation because then you can manipulate this into our familiar geometric series. So how we did it with this is I needed to factor out the 3. So this is 3. And then 1 plus x over 3. And it's very close to what I need. I just need a minus sign here now. So this is 1 over 3. 1, and I'm going to do my double negative trick. I have negative x over 3, and then that gets me back to the original. So now I have the form 1 over 1 minus something to plug into my formula. So therefore, I'll factor the 1/3 out front. And then I get the summation as n equals 0 to infinity. And then this is what I'm plugging in for my geometric series, this negative x over 3 to the n power. And then if I further break this up, this is 1/3 summation, n equals 0 to infinity. If I have a negative, here I'm going to break that up into negative 1 to the n. And then I'll have x to the n, and then that's a fraction that can be broken up into 3 to the n. And then this is going to be true for when this right here, the absolute value of negative x over 3, that needs to be strictly less than 1. But what that actually means is that x needs to be strictly between negative 3 and 3. And this is this series interval of convergence. OK, so now from here, what I'm going to do is I'm going to use this to get to the power series representation that I want. So now what this means, so I'll say therefore, ln of 3 plus x, well, that's the integral of this, right? Because if the derivative of ln of 3 plus x is this series, to get to ln of 3x, I need to integrate this. So I'm going to have the integral of, and then this 1/3, I'll just leave this out front. And I'm going to integrate this series term by term. So from n equals 0 to infinity of negative 1 to the n, x to the n, over 3 to the n. So I integrate that term by term. What that looks like is I have 1/3 as a constant. And I just pay attention to the x variable. So this negative 1 to the n is also a constant, as is this 3 to the n. Now I need to increase the power of x by 1, so backwards power rule. So that's n plus 1. And then I need the new power to be in the denominator, so n plus 1. So that's, I've integrated that. Then it's plus c, because I have this indefinite integral here. OK, so now I need to figure out what c is going to be. Here's how I'm going to do it. So what I know is that if I follow this whole chain of equalities, I know that the log of 3 plus x is equal to 1/3, basically the last thing I got, n equals 0 to infinity of this series right here. So over 3 to the n, n plus 1 plus c. I know that's true. This is valid within the radius of convergence here. It's certainly true strictly between negative 3 and 3. I have integrated this, so I may have also possibly introduced the endpoints as well. I'd have to check that, but I don't need to, because the value that I'm going to choose for x to find c is 0 again, just like the last one. I think that's the most convenient choice. So I'm going to choose x equals 0 because it's inside the interval of convergence. It's valid to choose that. The left side here is ln of 3. And the right side, if I plug in 0 for x, 0 times anything, and it's in the numerator, is just 0. So I'm just adding zeros for all of these terms. So this is the 0 series if I plug in 0. So that means ln of 3 is 0 plus c, but that means that c has to be ln of 3. So instead of this c right here, I can replace that with the constant ln of 3. And then this is my series representation for ln of 3 plus x. So it's very similar to the last one. I had to make an observation to get some kind of object that looks like this that I can manipulate into the geometric series. So when you're looking at something, think whether the integral or the derivative is going to get you to some kind of form that looks like this. All right, let's take a look at this last example now. So we're going to estimate the value of this definite integral to 6 decimal places. And I have written 0.000001 to remind myself that that's what 6 decimal places looks like. So we're going to estimate this, but we're going to use the power series representation to do that. So we'll work on the actual bounds in a second, but let's just take a look at 1 over 1 plus x to the 6th. Let's get a series representation for this. Very similar process to that. I'm going to do 1 over 1 minus a minus x to the 6th. And then I can use this to write out my geometric series n equals 0 to infinity. And this time I'm plugging in negative x to the 6th to the n. And if I break that up like I usually do, this is n equals 0 to infinity, negative 1 to the n, x to the 6n, if I multiply those together. And this is valid. Its interval of convergence is for negative 1 to 1. OK, so therefore, that means we have the integral that I want, the integral from 0 to 0.5 of 1 over 1 plus x to the 6th. I'm just rewriting the problem. That's equal to the integral from 0 to 0.5. Instead of this as my integrand, I worked so hard to turn it into this form. So now I'm going to plug this in place of this. So I'm going to have summation n equals 0 to infinity, negative 1 to the n, x to the 6n dx. I'm going to integrate this. And let's go ahead and do that. So I have term by term, as long as I'm in the interval of convergence, which I am. I'm from 0 to 0.5, which is in this interval. So if I integrate this, I'm going to have to increase the power by 1 for x. This is negative 1 to the n. It's a constant. This is x to the 6n plus 1 divided by 6n plus 1. I still have my summation symbol. Sorry about that. This is n equals 0 to infinity. So I've integrated this, and I'd have to evaluate this now from 0.5 to 0. So what is this equal to? Well, if you plug in 0 for the lower bound, no matter what term you're on, it's the 0 series again, just like I had over there, 0 plus 0 plus 0. So the 0 doesn't play into this at all. It's just this 0.5. So the first thing I would do is I would plug in 0.5, n equals 1. So I'm going to write it like this first. I want to show every step. So I'm going to have the series from n equals 0 to infinity, negative 1 to the n. And this is going to be 0.5 to the 6n plus 1 over 6n plus 1. So that's what happens when I plug in 0.5 for x, minus. And then I'm going to get 0. So this is the point I was trying to make. If you plug in 0 here, they're all going to be 0. All terms will be 0. So this series is just the 0 series. But now here, this is an infinite series. So for example, if n is 0, what do you get? You get 1 here. You get 0.5 to the first power over 1. Right? And then this is when n equals 0. And when n equals 1, you get negative. It's alternating. And then this would be 0.5 to the 7th power over 7 plus, and I'll do one more, it's 0.5 to the 13th over 13. And this would continue forever. However, I have to estimate within 6 decimal spots. So I'll use my alternating series estimate to take care of that. So what I found here is that, so I'll write it here. So it turns out that the magnitude of A3, so when n equals 3, when you plug that in, the A3, that term, we have that's approximately 4.77 times 10 to the negative 8th. So the magnitude of this term this is like 7 decimal places. This is very small. It's the first term you encounter where it's strictly less than the level of accuracy that I need. So I'll just say that. It is the first term which is within 6 decimal places. Or its contribution is within 6 decimal places of the overall answer. And as such, by the alternating series remainder theorem, once you find that term that ensures the error is within this amount, so this is the first instance where I'm within 6 decimal places, it turns out I just need up to all the previous terms. So I'm going to need A0, A1, and A2. And as long as I sum those first 3 terms together, I will be within the 6 decimal point accuracy that I need. So this final answer here, if I just take these first 3 terms, because that's going to be accurate enough, you get that is about, so this is adding these 3 terms together, it's 0.4988933. So again, you are only as accurate as the magnitude of the following term. That was the alternating series estimate theorem. And you can go back to the video on that if you need a refresher. But that's not what this whole problem was about. This problem was determining the power series representation and using it as an estimate. So, OK. I hope that helps with power series representations. In class, I'm sure we will do even more. Please reach out to me if you have any questions. And until then, I will see you next time. Bye.